ওকে, এই ক্লাসে আমি this is the class of optical diffraction part 5. So in this class I am going to derive the Kirchoff's diffraction theory and of course the Fresnel Kirchoff's diffraction formula for the diffraction. So let us first try to say something about the Huygens principle of propagation of a wave through any medium. So let us assume that this point is the source of light emitting, and this point emits some spherical wavelets which are propagating along this 360 direction, along any direction, and this wavelet, the spherical wavelet which are generating from this point, are obstructed at this point Q, which may be considered as a combination of two wavefronts. That is, this is the inner wavefront, and from this inner wavefront, each particle on this inner wavefront can be serve as a source of secondary wavelet, যেটা কিনা আমরা এই ছোট্ট ছোট্ট secondary wavelet দিয়ে I have shown those secondary wavelets, and these are the locus of all those points which are initially on this wavelets at some later instant of time. So this Q point is situated at a distance r. These are angle of diffraction, and this is the external point P at which I am going to measure the effect of this secondary wavelets due to diffraction, and it is situated at a distance r from this point, and we are going to consider a parameter, that is UR, which represent any kind of disturbance that are observed at the point P. তাহলে P পয়েন্টে যদি কোনো অবজারভার বসে থাকে, সে যে পরিমাণ ডিস্টারবেন্স ফিল করবে, that is represented by this UR function. Okay, এখন we all know that any wave can satisfy this differential equation, three-dimensional differential equation, del square psi equal to 1 by v square del square psi by del t square, where this psi has three spatial part and one time dependent function, and this psi represent any kind of disturbance basically in the medium. So as we all know that this psi may be some monochromatic scalar wave. So this disturbance and this psi is related to some disturbance, as the psi can measure monochromatic scalar wave. Okay, and this psi may be sometimes measured as electric field or magnetic field component, say for example Ex Ey Ez or Bx By Bz. Okay, now this as electric field, we sense electric field through our eye. So as our sensation goes for the electric field, so we are taking electric field component E, and this electric field component also satisfy this differential equation. So psi will be replaced by E in this equation. So this differential equation is basically Helmholtz equation. We already all know about the propagation of light through any medium that will be governed by this differential equation. এবং this E must have three components, Ex Ey Ez. So E must be a function of this. Now if you try separation of variable in this to solve this equation, temporal part that will have e to the power I omega t form of any wave. তাহলে monochromatic wave যদি সে তার angular frequency omega হয়, so electric field can be represented as a spatial vector, a spatial function u x y z, and of course e to the power I omega t. Now this is Helmholtz equation. This ux denotes the disturbance at any position xyz t xyz, and u is a kind of function that have a specific property. What are the property? That it must contain continuous first order and second order derivative. Okay, এবং যেহেতু this source can emit the spherical wavefront, so the secondary wavelet which is emitted at this point q once again becomes spherical. এবং in my previous video I can show you that although the plane wavefront are propagating along a direction, and when these plane wavefront are obstructed by any opaque region where some kind of transparent medium is there, small amount of holes are there, when the light propagating through that small opening, then those plane wave can generate some spherical secondary wavelet which through that opening. তাহলে এইভাবে আমরা প্লেন ওয়েভফ্রন্ট থেকেও স্ফেরিক্যাল ওয়েভফ্রন্ট জেনারেট করতে পারি। তাহলে কিউ পয়েন্টে যে ডিস্টারবেন্স অ্যারাইজ করবে, ইফ দ্যাট ইজ দ্য পয়েন্ট অফ ডিফ্র্যাকশন বা দ্য এজ অফ ডিফ্র্যাকশন আমি যদি বলি, তাহলে ওই পয়েন্ট থেকে যে ওয়েভলেট জেনারেট করবে দ্যাট ওয়েভলেট মাস্ট বি স্ফেরিক্যাল। তাহলে যদি এটা স্ফেরিক্যাল হয়, তো স্ফেরিক্যাল ওয়েভলেট আই ক্যান use this kind of equation which satisfy the Helmholtz equation obviously. So exponential spherical wave, a spherical wave have this form E0 R0, which is the amplitude portion, it is over IKR by R, which must satisfy the vector Helmholtz equation. Okay, এবং আমি এটা ধরে নেব যে the distance R is very large compared to the wavelength. Okay, and obviously যেহেতু R large, even K has got a value twice pi by lambda. Lambda is extremely small, of the order of 10 to the power minus 8 meter. So I can say that this KR must be very greater than 1. সুতরাং আমরা restrict করব আমাদেরকে R to the narrow range perpendicular to the polarization. Okay, এইবার আমরা এখানে একটা just pictorial representation নিয়েছি. These are the aperture through which diffraction is going to happen. এবং n is the normal over this opening. R হচ্ছে this is the point where I am going to measure the diffraction pattern. P is some kind of point, there is not an external point, basically this is the external point, এবং আমি এই external point কে radius করে একটা সার্কেল ড্র করেছি। ওকে, সো দিস আর দ্য কনস্ট্রাকশন। এইবার আমি আসবো এই কনস্ট্রাকশনকে কিভাবে আমি কাজে লাগাবো। তাহলে কি না, আমি প্রথমেই যে অ্যাপ্লিকেশন অফ কার্চফস ডিফ্র্যাকশন থিওরিতে যে অ্যাজাম্পশন গুলো ধরে নিয়েছি, কি ডিস্টারবেন্স ওয়েভ ফাংশন এবং তার গ্রেডিয়েন্ট contribute negligible amount to the integral except the aperture opening itself. তার অর্থ হচ্ছে ধরে নাও কোনো একটা ডিস্টারবেন্স এখান দিয়ে আসছে, তাহলে সেই ডিস্টারবেন্সটা when it is obstruct, that kind of disturbance which are coming towards the slit and it is obstructed by the slit, except the opening of the slit, everywhere the contribution will be zero. That is my first assumption, that is the disturbance of wave and its gradient contribute negligible amount, tends to zero, to the integral except the aperture opening itself. The value of disturbance wave function and its gradient will be same as they are absent of partition. তাহলে the wave function will not degrade anytime. It will provide same amount of disturbance whether the partition is there or there is a small opening through which the ray can pass. And third assumption is, as a spherical wave, that is obvious assumption, its electrical field vector will be E0 e to the power I omega t. এইবার আমি কি করব, আমি Kirchoff's diffraction theory derive করার চেষ্টা করি. So these are the picture. This is the source P0. At point R0 there is S wavefront, which is spherical wavefront, and each point situated on this spherical wavefront S can serve as a source point of secondary wavelet. তাহলে S এর যে আমার কার্ভেচার, এই S কার্ভেচারের উপরে অবস্থিত যে কোনো বিন্দু সেকেন্ডারি ওয়েভলেট তৈরি করার সোর্স হিসেবে ইউজ করা যেতে পারে বা সোর্স হিসেবে কল্পনা করা যেতে পারে. আই ক্যান অ্যাজিউম দ্যাট. এবং at any later time the wave front is moving to S1. Now I am going to calculate the total effect of diffraction at this external point P, which is situated at a distance B from this S1 spherical wavefront. Okay. Now any disturbance means component of electric vector and B. আমি obviously এটা আলোচনা করেছি. এখন শুধু এখানে just say about this picture. This is the contour integration over, I can integrate some vector field over this vector field or scalar field over this S surface, or I can we integrate some S prime surface. Now I am going to jump in some differential theory. So wave equation from Huygens-Fresnel principle we can put on a mathematical basis using an already known integral theorem which express the disturbance at any point P in the field in terms of the value of disturbance and its derivative at all points on any arbitrary closed surface S surrounding P. So I can do this. যে আমি P point কে সারাউন্ড করে যদি কোনো সারফেস থাকে, আমি ডিস্টারবেন্স at any external point P সেটাকে কিভাবে রিপ্রেজেন্ট করতে পারি না, as the value of disturbance and its derivative at all point. সেটা কিভাবে আসে সেটা আমি পরে দেখাচ্ছি. Now this is the Helmholtz differential equation, and electric vector can be represented as EXYZT. এবং আমি এই E vector কে তার যে কম্পোনেন্ট EX, EY, EZ এই টার্মে যদি ভেঙে নিই, and each component, any of this component EX, either EX or EY or EZ, can be expressed as a function as in terms of V, then del square V plus 1 by C square del square V by del T square equal to 0. This is a generalized form of this Helmholtz equation for the three individual component EX, EY and EZ, right? Where this VXYZT can be represented in this form. তাহলে এর যে স্পেটিয়াল পার্ট সেটাকে আমি ইউ বলে রিপ্রেজেন্ট করেছি. ইউ হচ্ছে কি ডিস্টারবেন্স অ্যাট এনি পয়েন্ট XYZ. তাহলে এইটা যদি ঠিক হয় তার এইবার আমি জাস্ট ডাইভারজেন্স থিওরেম অ্যাপ্লাই করতে পারি. হোয়াট ইজ ডাইভারজেন্স থিওরেম? না, let us take the that the function, the spatial function of disturbance u can have a continuous first and second order partial derivative, and if this derivative exists within and on the surfaces, যেটা আমি জাস্ট আগের ইমেজে নিয়েছিলাম, অন দ্য সারফেস, এই এস সারফেসের উপরে ইউ ফাংশনটার কন্টিনিউয়াস ফার্স্ট অর্ডার এবং সেকেন্ড অর্ডার ডেরিভেটিভ, পার্শিয়াল ডেরিভেটিভ, obviously that can exist. Then applying divergence theorem, we can say that the disturbance at any point which are lying within the surface S can be represented as sum of all the disturbance coming through that surfaces. Okay, now that is basically integral over any volume element V which is closed by this ds surface. So u del square u prime minus u prime del square u into dv. U prime is another function which have the same status as u, and u prime also satisfy the same continuity equation as u, right? Then from divergence theorem I can say about this n is basically outward normal, and the differentiation is taken inward to the normal S, which denoted by n cap. This is the direction of area, right? Now what is the value of this left hand side of this equation? From Helmholtz theorem I can replace del square u prime as minus k square u prime, and from this part del square u can be replaced as minus k square u. তাহলে এই দুটোকে যদি আমি রিপ্লেস করি, so left hand side of this differential equation will be 0, and obviously the right hand side must be equal to 0. So I can write this equation. Now as the spherical disturbance is coming and this is the distance s, the spherical disturbance which are arising from this point and reaching to point P must have the form e to the power IKS divided by S. That's why I am taking u prime as e to the power IKS by S. S is the distance from P to the point XYZ, right? Now we can construct another integral which is carried over surface S prime. তাহলে আমি যে দুটো সারফেস নিয়েছিলাম, ফার্স্ট সারফেসের উপরে আমি যে ইন্টিগ্রেশনটা করলাম সেটা হচ্ছে এস প্রাইমের ইন্টিগ্রেশন, ঠিক আছে, এস প্রাইম সারফেস। সো সে ফর এক্সাম্পল দিস সারফেস, এবং সে ফর এক্সাম্পল দিস সারফেস, এবং এস প্রাইম সারফেসের উপরে জাস্ট ইমিডিয়েট আফটার দিস যে টি টাইমে যে সারফেসটা তৈরি করছে, হোয়াট আর দ্য এফেক্ট অফ দ্যাট সারফেস বেসিক্যালি। সো দ্য এফেক্ট অফ দ্যাট সারফেস I can integrate over S prime, and the integration form will be just the same, u del u prime by del n minus u prime del u by del n into ds, and the direction of this normal of S and S prime surface will be same. অর্থাৎ S এবং S prime surface, যদিও এখান থেকে বোঝা যাচ্ছে না, যদিও আমি হয়তো ইমেজটা একটু অন্যরকম এঁকেছি বলে, but the direction of n and this n must have the same direction as surface S and S1 have the same direction of normal. So u and u divided by n. So when I integrate over this S prime surface, this will gives me integration S prime u del u prime by del n minus u prime del u by del n into ds prime. Now if we add all these two, that is the effect of this over two individual surfaces, that is S and S prime, and I can replace this u prime as e to the power IKS by S. Then the equation will be u del by del n e to the power I k s by s, as I replace u prime by e to the power I k s by s, minus e to the power I k s by s del u by del n dot ds equal to minus, that is integration over this s prime surface, where I replace u prime as e to the power I k s by s. So u del by del s e to the power I k s by s minus e to the power I k s by s del u by del n into dot ds prime. So this equation is right. Now I have to simplify this second equation. So how? Take any arbitrary radius of xi and integrate that surface, integrate s prime surface in such a way that s prime surface can be replaced by a solid cone. Okay, that is d omega prime. So ds prime can be replaced by xi square into d omega prime, and this radius s will be again replaced by xi. Okay, তাহলে if I calculate this integration over s prime, which is arbitrarily chosen as a sphere, and the center of the sphere is situated at the point P. তাহলে আমি যে এইখানে পয়েন্টটা টেনেছি in this part, so these are basically, যদি এটা spherical হয়নি, but this is sphere, this is the P point, point of disturbance, and this is the radius. Okay, এবং এই সারফেসটা যেটা আমি নিয়েছি that is basically s prime of radius r. তাহলে আমি কি করব না xi prime কে আমি arbitrary radius ধরে রিপ্লেস করে দেব, and the equation will be u e to the power I k xi by xi, s will be replaced by xi, and if you differentiate this term, now how can you differentiate this term? This del by del n represent the direction of normal. Okay, and the surface is, this is the radius. Now s1 basically the radius of the circle, sphere, that spherical wavefront are propagating. So direction of n, that is normal over this surface, and direction of s prime s, that will be same. So I can replace del by del n by del by del s. Okay, and if you differentiate this term, you will get I k minus 1 by s with the power I k s by s. So this will be the form, and again s will be replaced by xi, and ds prime for solid angle I can replace this ds prime by xi square into d omega. Now the integral over s, that is independent of xi. Okay, আমি xi কে যা খুশি নিই না কেন, I can enlarge the xi in sufficient amount, and I can make the xi very short, then the integration will be independent of xi. Now if you simplify this integration, you can get that integration omega prime u e to the power I k xi by xi into xi square. So this will be xi into d xi, some I k is there, and from second equation this will be xi square. So this part will be coming as this, and the third part obviously to the power I k xi into del u by del n xi into d omega. Now for first term and the last term, that is the first term this including this term, and the last term, this too contains the function xi, the variable xi, and I choose xi tends to 0. That is the limiting value of xi. Okay, তাহলে arbitrarily xi কে আমি এমন ভাবে চুজ করব যাতে কিনা the radius of the xi should be 0 কেন তার কারণ হচ্ছে I have to calculate the effect of all the integration over at any point p. So I should not make the radius of that circle or the radius of that solid angle so large that the space contains numerous number of points, but I have to calculate the effect of diffraction at any point where the point can be considered as a sphere of radius tends to 0. ঠিক আছে তাহলে যে পয়েন্টটাকে আমি কনসিডার করছি দ্যাট পি পয়েন্ট এইভাবে আমি কনসিডার করছি যে দ্যাট ইজ এ স্ফিয়ার of radius tends to 0. So the effect of these two integration becomes 0 and ultimately this u e to the power I k xi by d omega, this term survives. So u e to the power I k xi into d omega, as xi tends to 0, so e to the power I k xi equals to 1. So this will be u into d omega prime. Up is the independent function, so this will be 4 pi up. So up is 1 by 4 pi integration s u del by del n to the power I k s by s minus to the power I k s by s del u by del n into ds. So this integration is basically Helmholtz-Kirchoff integral theorem, right? And this up represent the disturbance at any external point p due to any second due to diffraction, right? Okay, so now I'm going to derive Fresnel Kirchoff's diffraction formula, which is just application of this Helmholtz-Kirchoff integral theorem. So what are the application? Let us consider this p is the source of primary wavefront and spherical wavelets are generating from this primary wavefront and that are propagating through the slit. Now this slit, as the disturbance are going through slit will generate same amount of disturbance, and that amount of disturbance are propagating through the measurement the observation point p, and I am going to measure the effect of that disturbance at that external point p. এইবার আমি কি করব না, this is the opening, this is basically a contour, and this contour is a spherical contour of radius r, keeping p as a center of this sphere. এবং আমি জাস্ট এইখান থেকে যে সমস্ত ভেক্টর গুলোকে পাবো, সে ফর এক্সাম্পল p হচ্ছে সোর্স পয়েন্ট, so these are the direction of propagating vector, these are the diffraction direction p, or that is observation point. Now the angle between these two is basically n into s, that is the normal to the surface, and obviously s vector, the diffraction vector, and these are the angle between n and r. So the disturbance that are arising from p0 is spherical, so I can consider ui incident at this point a as a e to the power I k r by r. Now there are some assumptions. What are the assumptions? That is, the wavelength of light must be very very less than the dimension of the apparatus. অর্থাৎ যে অ্যাপারেটাসটাই আমি এই ডিফ্র্যাকশন এক্সপেরিমেন্টটা চালাচ্ছি, obviously তার রেডিয়াসের চেয়ে অনেক ছোট, so lambda will be much much less than r and s, that is distance from q, distance of q from point p and p0, right? Now I am going to calculate the value of up at point p, that is disturbance at point p. তাহলে from Kirchoff's integral theorem which represent that the diffraction is basically up 1 by 4 pi integration of all sorts of diffraction over the surface, all types of surface. Now এখানে কি surface আছে? এখানে আমি there are 3 line integral over this arbitrary chosen ds surface. So integration obviously on this opening, integration obviously through this 2b surface, and integration over this contour c, and this will be u del by del into the power I ks by s into the power I ks by s del u by del n. এটা আমরা প্রথমেই Helmholtz-Kirchoff's integral theorem থেকে পেয়েছি। তাহলে I can replace this term with ds. There are some boundary condition. What are the boundary condition? That on A, that is when the ray is passing through this A opening, u equal to ui, and the first order differentiation with respect to normal to the surface, that will be continuous. And on B elsewhere, the effect of this spherical wave will be 0. So on B u will be 0 and del u by del n once again becomes 0. এবার যদি আমি ইন্টিগ্রেট করি, so ui again to the power I k r by r, so del ui by del n to the power I k r by r, I k minus 1 by r cos n r. n r is the angle between n cap and r cap. Okay, and this n is a direction of r, so I can differentiate this e to the power I k r by r with del by del r. Okay, and replace this two term in this differential equation. So I will get যেহেতু আমার স্ফেরিক্যাল ডিস্টারবেন্সটা যেখানে ইনসিডেন্ট হচ্ছে এখানেও যা ফর্ম দেবে এর ভিতরে যদি আসে, that form of spherical wavefront remains same. So this will be to the power I ks by s and to the power I ks by s del ui by del n. Now I can replace del ui by del n. This will be to the power I k r by r, এবং this n is the direction of r and this n is the direction of s. Okay, so the differentiation will be a to the power r k r by r e to the power I k s by s, I k minus 1 by s cos ns, minus e to the power I k s by s a to the power I k r by r, I k minus 1 by r cos n r to ds. এবং আমি বলতে পারি যে as lambda is small, then ik will be much greater than 1 by r and 1 by s. So ik minus 1 by s is this gives me ik, and ik minus 1 by r, this gives me ik. So the integration becomes up equal to ia by twice lambda. If I replace this term in here, so ia by twice lambda integration over s, this will be s e to the power ik r plus s divided by rs cos n angle between n and s minus cos angle between n and r into ds. So these are basically Fresnel Kirchoff's diffraction formula, and now I am going to apply this diffraction formula on this rectangular aperture. Say this is a rectangular aperture of dimension twice a and twice b, and these are two axes xi and eta. Okay, এবং আমি এই অ্যাপারচারটার উপরে জাস্ট ফ্রন্ট অফ ডিফ্রাকশন ক্যালকুলেট করব। এখানে একটা কথা বলে রাখি যে there is a basic difference between Fraunhofer and Fresnel diffraction. For Fresnel diffraction, I can assume that A is much less than R and S. That is, the opening will be very much smaller. But in case of Fraunhofer diffraction, obviously a square by lambda must be much greater than R and S. So these are two basically these are the difference, and a square by lambda is called the Fresnel number. Okay. So this equation is valid under condition of lambda less than r and s. Okay. Now I'm going to apply the Fraunhofer integral in case of this rectangular aperture. তাহলে জাস্ট এই ইন্টিগ্রেশনটাই আমি অ্যাপ্লাই করব e to the power I k p into xi plus q into s. Any arbitrary two constants are there and c is an arbitrary constant. So at any point which is at qp, that effect will be integration a e to the power I k p xi plus q beta into d xi d eta. So integration will be minus a2 plus a minus b2 plus b e to the power I k p xi plus q beta d xi d eta. তাহলে আমি এই ইন্টিগ্রেশনটাকে সেপারেট করে নিলাম. First integration is the integration with respect to xi, and the second integration will be integration with respect to eta. And equation gives me c e to the power I k p a minus e to the power I k p a by minus I k p e to the power I k q b minus e to the power I k q b divided by I k q, and this integration ultimately gives me first integration, this part will be equal to 2 sine kpa by kp, and second integration 2 sine kqb by qb, and this will be 4abc sine kpa by kpa sine kqb by kqb, and intensity will be sine square kpa by kpa sine square kpb by kpb. Now from this pattern আমরা বলতে পারি the diffraction pattern will be along two direction, along A and along B. So for rectangular aperture, this central will be maximum, as this represent QP will be equal to 0, this PQ will be 0, that is X and Y, and say minima at those points where KPA will be plus minus m pi and KQB will be plus minus m pi. So there will be central maxima and minima, maxima, minima, maxima along this direction, and minima, maxima along this direction and this direction. Okay, so along P and xi direction this is central maxima. Along xi direction there will be alternative dark and bright branch. Along negative xi direction, also along positive along in negative eta direction, and along positive xi direction there will be alternate dark and bright band, and there will be alternate dark and bright band. So the figure will be two-dimensional diffraction pattern. Okay, so these are the theory of rectangular aperture, that is diffraction through rectangular aperture. Okay.